Hello and welcome to the MapleSim webinar. My name is René Noack. I'm a senior application engineer from Maplesoft, and I want to talk about the news of our web handling library in the version 2024.2. So let's start with an overview of what's new in our version. So in the next minutes I want to talk about shortly the new features. There are some improvements in our library. I want to introduce our first app for the web handling simulation. This app is called Draft Formation Limit. And finally, I want to talk about a new sublibrary in our web handling library. This sublibrary is controls and drives. I would like to start with a short overview about our tool. For those who don't know MapleSim and our web handling simulation, so let's have a look at first on one example. Here you can see how it looks like in MapleSim. This is the main structure of models, of web handling models in MapleSim. We are talking about system simulation. That means we are considering the dynamic behavior of web handling process in meshing direction, and we can combine our web handling components together with other components. As you can see here, two different denser systems with a pneumatic part on it, and also some control structures in this model. And that's why we are talking about system simulation and also multi-domain simulation. As you saw, the web handling simulation came also with a 3D animation of your system, so that you can always have a look on a 3D view to check if your model has the right parameters, for example. MapleSim itself, our modeling and simulation tool, came with a lot of libraries, and the web handling library is one of the special libraries with a lot of components, what allows you to model very easily R2R process, a web handling process line. With MapleSim, it is possible to build and create web handling models and to do some analysis with those models. For example, there are a lot of apps and templates integrated in MapleSim to do, for example, a parameter sweep to evaluate different parameters. And also there is a possibility to use the connection between MapleSim and Maple to do a lot of customized pre and post processing with your models. And finally, it's also possible to generate code. And this means our models can be used in other environments. The main way to do this is to export an FMU, a functional mockup unit, and this opens the door to the world of simulation and other tools, as well as to do virtual commissioning and connect our model to a PLC and to test the control structure in the PLC, for example. If you had seen our last webinars about our former releases of our web handling tool, then you know the main structure of our library. It came with a lot of rollers with definitions for spans, winder, unwinder, and other stuff. All these components has theoretical background based on differential equations, and all of these components, for example, a roller has a lot of features in it. So this means you can use one component and, for example, use a roller in a denser system, and you can move it, or you can consider disturbances like eccentricities or unbalanced rollers. So this means each of these components are more than one component to consider different features, different defects and effects. In our current release 2024.2, there are some minor feature improvements. For example, now all of our spans has the same sensor output signals, means the web speed and also the tension in this span. In the older versions, these output signals are only available in the normal span definition, and now it's the same definition in our converting web span and also in our second web span. Then there are some improvements for the evaluation of slip conditions, and I want to talk about in the next slide. We got some customer feedback regarding our, how can I say it, our evaluation variables regarding slippage. We consider slippage based on the Kapstan equation in our rollers. And in the older releases, the user has the possibility to see the results in different speeds between roller and web. And there was also one summary variable, and this summary variable summary limit gave a feedback about the slippage itself. It says 0, there's no slippage, or 1, there is slippage. Based on the customer feedback, we changed this definition. So now it's a continuous changing between 0 and 1, and shows the range between no slippage and slippage, so that your user has the knowledge about how far away he is from the limit. A second summary variable called slip ratio is also now implemented in these rollers. It's also based on a evaluation criteria of a customer, and this variable defines the slip ratio based on the difference of the speed. That means it's the rotational speed times the radius minus the real web speed, and normalized also by omega times L. So this is some minor changings inside of the library, and in all of the components who can slip. Also for example, the detailed roller or the variable nip roller. As next, I want to present our first app for web handling in MapleSim. Maybe you remember there was a webinar in 2023 presented from our expert Steve Lang, and he was talking about a lot of issues in web handling and how you can solve it, and also he presented some equations as an approach to estimate the probability of troughs and wrinkles in a web line based on overtensioning as well as based on a misalignment of a roller. We took now these equations and put it in an app, so now it's possible to use this app. If you have created a model in MapleSim, a model from your system, then you can do a post-processing with this app, and do an analysis based on the equations and can check your entire line of overtensioning, and you can also calculate the maximal allowed misalignment angle before there is a probability to get troughs. I have an example here to demonstrate the capability of this app. You can see here a web line with an unwinder with a master speed nip roller and two auxiliary drives, and the unwinder is connected to a powder brake. And if I simulate this, you can see at first a 3D picture, and then you can see also I have here some tensions from different spans, and some of them have lower values, some of the spans have higher tension values. This is based on bearing losses, on the function and the control of the auxiliary drives and so on. If I open the app, at first you can find here again the references for the calculation base behind our app. And the first step is to load the model, to load the parameters of the model, and to define additional parameters in cross direction. Normally it starts with the same values then in meshing direction, but you can change it if you have these values. For example, the elastic modulus. And then after a simulation run, you get different results. The first diagram shows the misalignment angle, which is allowed before you get troughs in your spans. And the second diagram shows you the wavelength ratio, trough amplitude to wavelength ratio, and this is a criteria to evaluate the probability to get troughs based on overtensioning. And you can see here two limits, more harder limit with 0.05 and a more softer limit for 0.075. These limits came from the paper where the calculation base is published, and it shows you if you have spans in your system where you have the probability of overtensioning. And now if you see this, now you can check your system, reduce the acceleration if you start the machine, add more torque on your auxiliary drives to reduce the tension, for example, and do other stuff to avoid overtensioning. You can use this app, change parameters and run it again and check if it would help. Maybe you have to think about other materials, something like this. And finally, you can also export the results of this calculation into an Excel sheet so that you can use it for internal reports, for example. Okay, then let's start with the main part of the presentation, our new sub-library inside the web handling library called Control and Drives. As you can see here, the sub-library, you can find different controllers with a general description comparable to controllers what you can find also in PLCs, but in a more general way. And these controllers can be connected to drives, and you can see also here some two different drives for different simulation concepts, and the powder brake for the unwinder. So what was the reason why we decided to develop such a sub-library? Why do we need these components? As you know, it's very easy to create a model of a R2R web line in MapleSim. You can create a dynamic model with rollers, with bands, with unwinders and winders, denser systems, rotational denser, linear denser, and so on. That's very easy to do. And then is always the question, how can the model be controlled? How can the simulation be stimulated? And for example, you can see the 3D picture of the same model. And yeah, the question is, how can we insert the control strategy for the simulation? We need a master drive definition for the webline speed. We need tension control with a measurement from a load cell, for example, and maybe we need a position control for from a denser feedback to control the unwinder. And before this release, the way to do this is to insert components from our signal blocks library to implement the controller. You can see here this components is a PID controller, for example, and all of these blue components came from the signal blocks library. And also you can see this gray components here. These are very perfect drives, speed drives, to drive all the rollers with a defined speed. But each of these steps needs a lot of effort. You have to drag and drop the right components, connect it, define all of the parameters in these components. Personally, I'm thinking each time about, should I multiply or should I divide my web speed with R to get the rotational speed. This is a very easy task, but then the next question is, how can I be sure that I define the right signs? Do I need a higher speed or a lower speed to get more tension? And this is connected to the order of my system, first drive or sensor, sensor or drive, where goes the tensioning direction of my denser system. All of these questions influences the sign definition in control loops. And this needs time, and our idea was to create components to save this time to do the real work with the simulation. So what was the target for the development of these components? At first, it should be very compact components, easy to use. It should be possible to save time for doing the modeling, and also these components should be usable together with specific components or customized components which are developed from our customers. And if we have a look at first on the level of tension control, there are two components in this library. One is a speed motor, one is a powder brake, and also the matching components for the control side, two tension controllers and two position controllers for dancers, rotational and also for a linear dancer. And how can these components be used? At first, the speed motor needs the line speed, the web speed as an input signal, and so it's clear that the user should define the roller radius or can turn on a second input signal for an external radius, what means you can combine it with a winder or an unwinder component. And also it is possible to use SI units as well as imperial units for these control signals. So if you are more familiar with a different kind of units, you can also use this. And that's the same for the control side. All our controllers can use the defined units. The attention controller uses a feedback signal from a load cell. That means any tension signal from your model can be a feedback signal for this controller, and the position controller needs the connection to the rotational point of a dancer, or if it's a linear dancer, the point of the linear actuation. How does it look like in our model now? At first, we define our master speed drive, just connecting it, the speed motor with the nip roller on the 1D port, and use a ramp. In this case, it's just one ramp for the definition of the speed signal. And on the right side, there is a tension control for the winder. The same component, speed motor, is used. The option for the external radius is activated, so it needs a measured radius here. And the input signal for the speed motor is not only the master line speed, it's also the sum of this line speed with the output of a tension controller. And on our left side, there's a dancer, as you know, and this dancer rotation point is connected to our tension controller for the rotational dancer, and the output of it is connected again with the speed motor. So in total, the effort to define this control loops and place the right components in it, it's now very easy, and you can work now on the parameters and test different parameters for the controller settings. You can also define new or changing in this control loop. For example, if you have no radius measurement on the unwinder side, and there's a constant parameterization of the diameter here, how does a position controller of my rotation tensor work in this case? So all of this is now possible. And again, you can define, normally the default value is for the master speed, for example, is meter per seconds. But if you want to use a different definition, different unit, for example, feet per minute, then you can just define this input signals in your unit. Okay, then let's have a look in MapleSim itself. How does it look like? On the left, you see the web handling library with a new sub-library, drives and controls, the powder brake and the speed motor, what I presented here, and the tension controllers and some additional stuff, what I want to explain later. So let's start the simulation, and we want to have a look on the components. You see here the speed motor, this input signal, the web speed, and the rotational 1D port is connected to our nip roller. Let's have a look on the settings. You see the diameter is defined, and if we activate the option for use input, for example for winder, then you get another input. Also, it's possible in this component to define a very simple motor dynamic modeled as a second order filter. That means you can define the frequency and also the damping ratio of the motor dynamic, and it's possible to define a visualization of this motor in the 3D view. So if you have a look on the results, at first on the 3D view, you see now these motors can be visualized in this 3D view of your system, just for a better understanding. It's not a functional feature, it's more for discussion with colleagues, for example, where the motor are and so on. Yeah, and as you know, if you use this library, you get a lot of results. Just want to change a view. For example, you can see here the tensions. The red line is the right side, the left, the green one is from the unwinder web speed, and for example, the rotational angular of the dancer. And if we zoom in, for example, in the web speed, you can see the different speed definition. Red is our master speed, and green and yellow is the local speed what is changed or influenced by the controllers. Yeah, what's happen if we deactivate the controller for the dancer, for example? You see here it's just a P controller used, and I changed the gain to 0, so it's not active right now. And I start the simulation again. And for the waiting time, let's have a look on the controller parameters. At first is always to define the order. It's sensor and then the drive, or the drive and then the sensor. And the second is the controller setting itself. You can change controller type, P controller, PI, under the PID controller setting. You can define the control parameters, define limits, and at least, as I talked about, there is the possibility to define the units, I/O units, for the inputs and output signals of these. If you don't want to use default settings. Similar on the position controller for the dancers, the setting for the order and also for the tensioning direction. And if you have a look on the simulation results, now we can see what's happening with our tension. You see a drift in this tension signal for the unwinder, and also a drift in the dancer angle. And if I start the animation, you can also see this animation, and dancer is moving. So this was expected because I have no feedback and no feedback in this model. Okay. Yeah, all of these components has his own help page with explanation of the used controller settings, the component, what is used inside this component. Also an explanation about the tensioning direction for this position controller for the dancer, for example. And you can see here the list of all controllers, and here the general page for the concept of this sub-library inside of web handling. And you can see the same model what is explained here, what you saw in the simulation. And also there are some references where the main ideas come from to develop this tension controllers. And yeah, there is a second level of control. Maybe it's needed sometimes, and you want to simulate also the lower control level. I would say that means now it's also important to see the influence of your underlying speed controller. Then it's also possible to do this in MapleSim, and I want to show it in the next coming slides. And the way to do this is just to replace the speed motor, the blue one here on the slide, with torque motor. The torque motor needs a torque input signal. and gives you also a feedback signal for the rotational speed. And to complete this, you need also a speed controller, and you can see here two components, speed controller for normal roller, I would say, and a second one if you use this for a winder or unwinder connection, then you have additional input of the radius. These components have similar approaches than what you can use in a PLC. It includes a speed controller also as a PID controller, and this includes inertia compensation. So that means there's a feed forward part inside of this controller. And also this component has the same possibility like the others to define the unit on for your inputs and outputs. So all of these components are compatible to each other and makes it very easy to use. And what is inside of these components? At first, the torque motor. It includes also a model of your driveline, what means you can define a gear ratio, you can define inertias from the motor, from the gear, or if known, also from the shaft. And it's possible to define motor losses here. And yeah, the speed controller, as I said, has a feed forward part at this stage. It's inertia compensation included. That means the controller, the speed controller here needs geometrically information from this roller. And also the speed controller for winder or unwinder needs information of the web on this drum. And so that's the reason for the feedback signal of the diameter here, for example. Yeah, and what you have now is a very compact model. You have more details here than in the version before. You can combine it with your own components. It's also possible, but what you get is a very fast way to model control loops and also to have the overview about your entire line. Yeah, and what are our next steps? At first, I would like to hear your feedback of the usage of these components. We have some plans to extend it. For example, friction compensation for the speed controllers. Maybe gain scheduling for the control parameters. It's also often used method and PLCs, and new components for sure. For example, right now it's all the tension controls are based on speed. That means the output of a tension controller is speed. But you can also have a tension control based on a torque output. So this is also one of our next steps. And also what's happening if you want to use a more real concept. That means you have, for example, different disturbances on your signals. For example, what's happening if your sensor has some effects, and how does it work together with the controller. So this is a path for our next steps regarding the drives and controls. Yeah, this was my short overview about the news in our web handling release 2024.2. And yeah, you can see we can help you to analyze different aspects of role-to-role system. If you are interested, please contact us and we can organize a meeting and do a more deeper look inside our tool. And yeah, all what I can do is have a nice day and thank you for your attention.